Good evening, everyone. Today, welcome you all in my next class of matrices. In my last class, I have discussed with you what is the meaning of addition, how to add two matrices. To add two matrices, it is necessary that the matrices should be comparable. That means they should have same order. So whenever you add two matrices, that means their corresponding entries are to be added. Multiplying a matrix by scalar also we have seen. Whenever you multiply a matrix by scalar, that means each entry of that matrix get multiplied by that scalar. Scalar means non-zero constant. Now today we will discuss the algebra of operations on matrices. The first is addition. Whenever we talk about addition algebra, the first property comes closure property. What do you mean by closure property? Like we know that sum of two natural numbers is always a natural number. That means we say that set of natural number is closed under addition. Similarly, if you take any two matrices and if you add them, the resulting is also a matrix. That means addition is satisfying closure property, or we can say that the family of matrices is closed under addition. Means whenever you add two matrices, resulting is again a matrix. For example, if A and B are two matrices of same order, M cross N, you know that resulting is also matrix of the same order. Only their corresponding entries are being added. So it's also a matrix. Say it's a CI. So it's also a matrix. It belongs to the family of matrices. So sum of two matrices always a matrix. We call that the family of matrices is closed under addition. Now the next property comes commutative property. This also you know very well. Like addition satisfies commutative property in the set of in case of real number. What does it means? If you add any two real numbers, order doesn't matter. Similarly, here also, if we add any two matrices, as the entry of matrices are either real numbers or complex number, both satisfies commutative property and addition. So, for example, if you add these two matrices, it's a resulting matrix. But as the entries are real number, we know that this can be written as same as, and now we can again separate it. What it means, it is equal to B plus A. So whenever you add two matrices, order doesn't matter. That means addition satisfies commutative property. Next comes associative property. As you know, under addition, real number as well as complex number both satisfies associative property. So same is true for matrices also. It's very easy for you to understand, no need to prove it. Next comes existence of identity. Like which number is the identity element? So for every operation there is an identity. For example, if we talk about real number, if suppose A is any real number, so what we should add to A so that you always get A, right? So it's 0. Right, 0 is called identity for addition, right? Similarly, for any matrix, if A is a matrix, then there exists always a null matrix. So all the entries are 0, so that if you add them both, the resulting is the same matrix. Always we know that. For example, 2 minus 1 plus the null matrix 0, 0, in the same order, resulting is what? 2 and minus 1. So null matrix is called the identity for addition. Now next comes inverse, existence of inverse. Now for existence of inverse, it is necessary that there must be an identity. Then only you can define the inverse. For example, you know that 0 is identity for sake of real number. That means, now how to define inverse? If you add two numbers and if the resulting is identity, then both are known as inverse of each other. For every element, the inverse is different. For example, what we should add to 2 to get the identity 0? So it's a minus 2, irrespective to the order. So that means 2 as well as minus 2 both are called additive inverse of each other. 1 by 2. What we should add to 1 by 2? Minus 1 by 2. So that result is identity, right? So identity is one only for entire set corresponding to one operation, right? Where the inverse is different for each different element. Likewise here also, for any matrix A, there exists a matrix negative of A, such that if you are adding A and negative of A, irrespective of order, resulting is a null matrix, right? What is the negative of a matrix? We have discussed in the previous class, multiplying a matrix by minus 1. So for example, if I say here a matrix minus 3, 0, 1, 2. So what is its additive inverse? So 3 minus 1, 0 minus 2. So that whenever you add them, resulting is a null matrix in the same order. So both are called additive inverse of each other. This is the algebra of addition. Clear? Any doubt about how to add two matrices and what are the properties of addition on matrices? Sum of two matrices is always a matrix. If we add two matrices, order doesn't matter. That means it satisfies commutative property. It also satisfies associative property. For additive inverse means null matrix is in additive and its identity, and for every matrix its inverse is called the additive inverse. Now the next operation is very important, that is multiplication. Now whenever you have to multiply two matrices, so A is a matrix Aij order m cross n, B is a matrix Bjk of order n cross b. Now AB is possible. So what is necessary to multiply two matrices? If you want to multiply A by B, the number of columns of A must be same as the number of rows of B. Number of columns of A must be equal to number of rows of B. So number of columns, rows multiplied by columns. So number of columns of A must be equal to number of rows of B. Then we can multiply A by B and AB is possible. But here B is not possible unless P equal to M. Right? So it means it is not necessary that if AB is possible, BA will also be possible. Right? So if possible, if you multiply two matrices, yes, product of two matrices is always a matrix if their multiplication is possible. So it's a closure. But when it's a commutative property, obviously it's not true. Commutative property means AB is not always equal to BA. Why? Because AB may exist, BA may not exist. For example, if I write a matrix 2 minus 1 0 1 2 3, and the other one is 0 1 3. So what is the order of this? 2 rows 3 columns, 2 by 3. Here 3 rows 1 column, 3 by 1. Right? So A can be multiplied by B. Why? Because these are equal here. Number of columns of A is same as the number of rows of B. So AB is possible. Now how to multiply and how to obtain AB? And what will be the order of AB? So order of AB will be M cross P, resulting. So whenever you multiply AB, and if it is possible, resulting will be a matrix of order M cross P. M cross P. So like A is a matrix of order 2 by 3, B is a matrix of order 3 by 1. First you check whether AB is possible. Yes, how? Because the number of columns of A is same as the number of rows of B. So we can multiply. Now when you are obtaining the result, what will be the matrix order? What is the order of the resulting matrix? It will be 2 by 1. That means 2 rows, 1 column. How to obtain this? Now we start with row. We start with first row, first column, first row, second column, first row, third column. Likewise, we multiply and complete the first row of resulting matrix. Then we start with second row. Second row, first column, second row, second column, second row, third column. Likewise, we obtain second row in this matrix, and the process continues. So here we take the first row, first column. And how to obtain the first row, first column, 1 position here. So we multiply the corresponding entries, first entry of row by first entry of column, second entry of row by second entry of column, third row entry of row by third entry of column. The result is the entry here. So 2 into 0 plus minus 1 into 1 plus 0 into 3. Right, now there is no other row, so process stops. Now second row, first column. So gives us second row here. 1 into 0 plus 2 1s are 2 plus 3 3s are 9. So resulting is minus 1. It's 2 plus 9 11. This is how we obtain AB. Where it is A, it is B. But can we obtain BA? What is the number of columns of B? 1. What is the number of rows of A? 2. So they are not equal. That means BA is not possible. AB is possible, but BA is not possible. I take some more example to explain you the matrices multiplication. Suppose A is a matrix. It is 2 rows, 3 columns, 2 by 3, and it is 3 by 3, 3 rows, 3 columns. So can we multiply this 2? Yes, because this is identical. And what is the order of the resulting matrix? 2 by 3. That means we will obtain here 2 rows and 3 columns, 6 entries. 2 by 3, 6 entries you will obtain. How to obtain the first entry? 1 1. So this first row, first column, first row, second column, first row, third column. So first row, first column, 2 2s are 4. 4 minus 1 3. 3 plus 0 is 3. First row, second column. So minus 2 minus 4 plus 0 is minus 4. First row, third column. 2 into 0 0 plus minus 1 into 3 minus 3 plus 0 is only minus 3. Completed AB. Now second row, starting with second row to complete here. Second row, first column, second row, second column, second row, third column. So second row, first column. 1 into 2, it's 2 plus 2. 4 plus 9, 13. 1 into minus 1 is minus 1 plus 4, 3 plus 3, 6. 0, 6, 0, 6. This is how we obtain AB. Right, but we can't obtain BA here. Again, same rule, you know. What we have seen that if AB is possible, if you can multiply A by B, then the product of two matrices will always be a matrix. That means if it is possible to multiply two matrices, the matrix multiplication is closed. Commutative property, AB need not to be equal BA always. So that means commutative property does not satisfy, not necessarily. Maybe, may not be, depend upon the situation. So it's not commutative. Third, second, associative if it is possible to multiply three matrices in the order, then obviously you can easily check condition that multiplication should be possible. A multiplied by BC will be same as AB multiplied by C, provided the multiplication is possible. Now comes existence of identity. That means for any matrix A, we must find out another matrix B such that A multiplied by B or B multiplied by A must be equal to A always. Then B is called the identity for A under multiplication, right? So which is that matrix? So here the identity is possible only for a square matrix, not for all the matrices. Right? That means if A is any matrix, for any square matrix only you can find. For any square matrix A of order M cross M, there exists identity matrix also of order M cross M, simply denoted as IM. And you know that identity matrix, so that if you multiply it by A by I or I by A, the resulting is always equal to A. Identity matrix means it's a square matrix, then it's a diagonal matrix, then it's a scalar matrix whose each entry of the diagonal is 1. It's called a unit matrix. For example, 1 by 1 identity matrix is 1, 2 by 2 identity matrix 1 0 0 1, 3 by 3 identity matrix. So these are called identity matrix. So if you multiply any matrix with this of the same order, resulting in the same matrix. This we can illustrate through example. For example, I will illustrate one example. For suppose A is a matrix here. Then an I is the identity matrix of the same order. That means 1 0 0 1. We have to verify whether A into I is same as I into A and is equal to A or not. So let's try A into I. 2 minus 1 4 3 1 0 0 1. First row, first column. 2 ones are 2 plus 0, it's a 2. 2 into 0 0 minus 1 minus 1. 4 ones are 4 plus 3 into 0 0, that means it is 4. 4 into 0 0 plus 3 into 1 3, it's 3. So A into I equal to A. Let's try I into A. 1 0 0 1. 2 minus 1 4 3. Resulting, you see now what it comes. First row, first column. It's 2 plus 0, it's 2. 1 into minus 1 minus 1 plus 3, it's minus 1. Then 0 into 2 0 plus 4 is 4. 0 into minus 0 plus 3 is 3. So it is also equal to A. So we have verified this. That means for every square matrix there exists an identity, but it's not true for all the matrices, only for square matrices. In my next class I will explain you about the inverse of a matrix as identity there, which matrix and how to find the inverse, right? That is my next class, right? So have a recapitulation of all these concepts and practice the questions based on addition, subtraction, scalar multiplication and identity matrix. So have a nice day all of you.